All right, guys, this is lesson 3 of chapter 14. This is on thermochemical equations. These equations are exactly like other chemical equations, except they involve the energy of the reaction as well as the reactants and products. And just like other equations, we can use these thermochemical equations to do some stoichiometry. So we're going to look at how thermochemical equations are written. Look at the energy lost and gained during the changes in state, and also how is heat that is absorbed or released in a chemical reaction calculated. You may have noticed that there is a chapter 14 lesson 3 assignment that posted this morning. So that goes along with this lesson. So if you bring that up, then we can work that through together. Some new vocabulary here: thermochemical equation, enthalpy of combustion, molar enthalpy of vaporization, and molar enthalpy of fusion. So these are some new ideas that we'll get into as we go through this. Remember, a combustion reaction is one in which a substance reacts with oxygen, releasing energy in the form of heat and light. That energy we usually say is fire. So anytime there's a combustion reaction, there's going to be fire involved. It's one of the 5 types of chemical reactions that we learned about earlier in the year. We learned about synthesis, decomposition, single replacement, double replacement, and combustion. So a thermochemical equation is a balanced chemical equation that includes the physical states of the reactants and products and the energy change, usually expressed as the change in enthalpy, or delta H. Change is the delta, enthalpy is symbolized by H. So this is a chemical equation right here. This is glucose being reacted with oxygen in a combustion. So we're burning sugar here, and we're producing carbon dioxide and water. Notice they all have coefficients, so that is a balanced chemical equation. And it tells me the enthalpy of combustion. So delta H is the enthalpy of the reaction. It's the change in energy as the reaction takes place. The enthalpy of this reaction, which is a combustion reaction, is negative 2,808 kilojoules. That's the reaction. Now we can write this reaction several different ways. We can say that C6H12O6 plus 6 O2s yield 6 CO2s plus 6 H2Os. And we can say plus 2,808 kilojoules. Now, this minus right here means that energy is being released from the reaction. Well, anything on the right-hand side of a chemical equation is being released from the reaction. The reactants go into the reaction. The products exit the reaction. And so we can put this, because it's negative, we can say that energy is exiting the reaction, so we would put it on the same side as the products. So both of these equations, the one at the top of the screen and the one at the bottom of the screen, both of these equations tell us the same information. Had this sign been positive, then we would have put it on the reactant side of the chemical equation. So here's 2 more examples. I have iron and oxygen forming iron oxide, and I see that the negative energy here tells me that we could rewrite this right here, with the negative energy being as a product exiting the reaction. Notice that in this second reaction here, the energy here is positive. It's a positive value, and we can rewrite that equation down here at the bottom with the energy as a reactant. So when you look at a delta H, so when we look at these delta H's here, you look at the sign, and if the sign is negative, then the energy is a product of the reaction. If the sign is positive, then the energy is a reactant, or is a requirement for the reaction. So it's going to show up on the reactant side. One of the most commonly used thermochemical equations is the enthalpy of combustion. The enthalpy of combustion is the enthalpy change for the complete burning or combustion of 1 mole of a substance. The value for the standard enthalpy of combustion, this means that the energy change takes place at a standard set of conditions. So here's a table for the standard enthalpies of combustion of some common organic compounds. Methane is natural gas that we cook with in our homes. Propane you might use for a grill. Glucose is a simple sugar produced by plants. Octane is what we burn in our gasoline. And sucrose is just normal table sugar. And so we can see their formulas here, and then their enthalpies of combustion. Notice they're all negative. All combustion reactions are negative. So all combustions have a negative delta H. In other words, they always release energy. Well, that makes sense. If I light something on fire, it's going to produce heat and light, flames. And so that idea there is showing that the energy is being released from the reaction. When a substance changes state, energy, usually in the form of heat, is either absorbed or released. Therefore, the enthalpy of a system is going to either increase or decrease. So if we have something like a block of ice and energy goes into it, we know that that ice is going to warm up and it's going to create a pool of water around it because it's going to start to melt. And so this idea of a ice or a block of ice absorbing heat causes it to change state. If I have liquid water and it is to cool down and it releases heat, well, then it's going to freeze. The molar enthalpy of vaporization is the amount of heat required to vaporize from the liquid to the gas state 1 mole of a liquid. So if I have 1 mole of water, which is about 18 milliliters, so that's 1 mole of H2O, then the heat of vaporization, so if I look at this table down here, the delta H of vaporization is 40.7 kilojoules per mole. So for every 18 milliliters of water, which is about the volume of 1 mole of water, I would need 40.7 kilojoules to turn it from a liquid to a gas. The molar enthalpy of fusion is the amount of heat required to melt 1 mole of a solid substance. So if I had 1 mole of H2O as ice, as a block of ice, then it would take 6.01 kilojoules per mole to melt it into the liquid state. So we can actually use these values to help us determine how much energy would be required to turn liquid water into steam or turn ice into liquid water. The thing is the amounts here, if you make them negative, then that's the amount required for the reverse process. So if I had steam, if I had 1 mole of H2O as a gas, then the negative 40.07 would turn it into a liquid. It's the opposite process. If I had 1 mole of water as a liquid, then it would take negative 6.01 kilojoules per mole to turn it back into a solid. So if we make these negative, then it's the reverse process. But as they're written as positive values. So this is going from liquid to a gas, and this one is going from solid to a liquid. If I make them negative, then the arrows would go back the other way. With the enthalpy of vaporization and fusion, we can calculate the change in enthalpy of other common state changes, and I've just mentioned that earlier. So the delta H of vaporization is equal to the negative delta H of condensation, because that's the opposite process. Delta H of fusion is going to be equal to the negative delta H of solidification, which is the opposite process. So this is melting, this is freezing, this is condensation and vaporization, which is the way you're used to looking at it. So you can see here vaporization and condensation are reverse processes. You can see that negative sign showed up there and here, but numerically they're equal. All right, so let's try one together. How much heat is needed to convert 147 grams of ethanol from a liquid to a solid at its melting point? Well, our delta H's are in kilojoules per mole. So we don't have moles, we have grams. So the first thing we're going to have to do is take 147 grams of ethanol, and we're going to have to convert that into moles. So the molar mass of ethanol is 46.07. Ethanol is C2H5OH, so I just added all those up. And that's going to be equal to 1 mole of the ethanol. All right, so we just do a little calculation here. 147 divided by 46.07, and that gives me 3.19 moles. So if I have 3.19 moles of ethanol, for every 1 mole of ethanol, I have, and I'm going to use my table here, so I'm going from a liquid to a solid. So the heat of fusion of ethanol is 4.94. So for every 4.94 kilojoules, that's how much it takes for solid to liquid. But this is going from a liquid to a solid, so we need to make that negative. So my 3.19 times negative 4.94, and that's going to equal negative 15.8 kilojoules. All right, and that's the answer to that guy. You just got to keep track of what's happening. For heat of fusion, that's solid to liquid. The heat of vaporization here is liquid to gas. And if you're doing the opposite, as we did in this example, you have to make it negative. Now, I could have put these two together as all one dimensional analysis. I could have said 147 grams. For every 46.07 grams is 1 mole. And for every 1 mole, I have negative 4.94 kilojoules. So that these two combined could be combined as just this guy right here. All right, so that's how those are solved. So go ahead and do some on your own. Pause the video and do numbers 5 and 6 on the worksheet. All right. The enthalpy of combustion, fusion, and vaporization can be used to calculate the amount of energy available during a reaction. So here's one. We already did fusion and vaporization, so now let's look at the enthalpy of combustion here and see how it can be used in much the same way. So this says we have 54.0 grams of glucose, which is C6H12O6. And this is going to be almost the exact same calculation as the one before. We're going to say for every, and we have to figure out how many grams there are in 1 mole of glucose. All right, that's 180.18 grams of glucose in 1 mole of glucose. And then we're going to look here, we have 1 mole of glucose and negative 2,808 kilojoules. So for every 1 mole of C6H12O6, we produced 2,808 kilojoules. So now I can cancel grams with grams, moles with moles, and I'm left with kilojoules, which is what I'm asking. How much heat is produced? Well, 54 divided by 180.18 times negative 2,808 equals negative 841.6 kilojoules. So all we're doing is we're using the delta H of combustion. We're using that value as a conversion factor. And everything else is done the same way we would do stoichiometry. If we were trying to figure out how much of a product were being produced, well, we figured out how much of the product heat was produced. All right, so now do numbers 7 and 8 on your own. That's the end of lesson 3. Remember that I'll be online tomorrow at 10 a.m. If you need help, jump onto the office hours. Feel free to shoot me an email, and I hope everyone's doing well. Don't forget there are 2 lessons this week, so take a look at Chapter 14, Lesson 4 next.